Hi, my name is Ahmed Nahas, an ECE freshman, and I'm really excited to present my team's honors lab project for this semester, where we worked on smart glasses for the visually impaired. Now, I actually attempted this project several years ago. It all started in 2018 at an awareness event when I met a really bright 13-year-old child named Yasser. Unfortunately, Yasser had lost the grace of sight, and at the time, I was really saddened and frustrated to see that with all of our current developments in science and technology, the best we can do was develop a white cane for the visually impaired, a stick among today's technical and scientific marvels. And this to me was really frustrating. And at the time, after several months of research and investigation, I set out to find a solution. After learning the basics of Arduino prototyping and circuits, the idea was to combine both ultrasonic sensors as well as vibrating motors to create a sense of spatial awareness for the visually impaired. And after several months of testing it and getting it to work, I finally was able to test it with Yasser and his friends at the local high school. And to see their smiles was just more than enough to push me forward with the project. I'm really excited to currently be working with five really talented students at Illinois, where we worked on reimagining the concept from the ground up, as well as developing it from scratch. So our goal was really ambitious, and it was to work towards a solution that is cheap and cost effective, convenient and well designed, as well as fully functional. And this includes both the input with the sensor as well as the output with creating an effective spatial awareness solution. And throughout the next few minutes, my team will share our plan, the design process, uh, the specific elements and the challenges we faced with each, and then finally our results and next steps. I'll pass it on to you.
Hello, I'm Yo-Yo Yu, and I will talk about the plan and design of the system. We have made a three-step plan, just to do the prototype on Arduino on a breadboard, and then transform all of the functionalities and coding to Attiny. Finally, we'll design a printed circuit board so that we can transform the whole system into a downscaled system, which will be fitting into the 3D printed glasses. This is the design block diagram that we have made. This system has been split into four parts: input, control unit, output, and power supply. The input includes the ultrasonic sensors and its firmwares. Control unit includes the Arduino and Attiny, along with all of the logic code that the system will operate on. The output includes the earphone that the user will wear and get the sounds according to the location of the object. And the power supply is just the battery, which will provide power to the system. Each of these sections, along with the difficulties that we encountered, will be explained later.
Hello, this is Ayush Sharma, part of the group for creating the smart glasses, the ECE Honors Lab, and I'm going to talk about the input devices which we use in our project, which includes the sensors, printing the circuit board, and creating the logic gates. And as for choosing the ultrasonic sensors, we initially decided on using CH201 sensors because of their really small size. They were 3 mm by 3 mm, their long range and high power efficiency. We used the datasheet of the CH201 sensor as follows. We noted down the operating voltages and the temperatures so that no sensor will get burned. We understood the pin distribution, which helped us design the circuitry to connect the sensors to the Arduino and the outputs. And the soldering instructions were also in the datasheet, which helped in the final step of soldering the sensor to the PCB. And the way we used the open source software documentation was as follows. The header file soniclibrary.h was given, and it contained all the functionality definitions of this sensor, including how to toggle modes, initializations, and it was a really extensive library. But not until after researching and experimenting a lot that we found that there were a lot more difficulties than we initially anticipated. Like, it was really difficult to interface this miniature hardware and integrating the complex software documentation with the other elements of our circuit. In terms of designing the printed circuit board, the sensor turned out to be really hard to integrate in our current hardware because the pin size were really small. It was literally smaller than the width of the wires, and there was no scaffolding for the sensor whatsoever. This meant we needed some kind of intermediate board to mount the sensor on and connect to the breadboard. So we decided to print a basic breakout board using the Eagle CAD software. None of us had any previous experience with printing circuit boards, so it was a truly eye-opening experience, and we learned a really new software, Eagle software, completely on our own. And we designed the basic symbol and footprint of the CH201 sensors, and we also printed a few circuit boards, the breakout boards. But because we were really new to this field, we made a lot of mistakes every now and then, because you need to get every drill, every hole, and every wire in just the right place to make the circuit work at full efficiency. And I needed to get the dimensions just right and the pins in the right places, and I made a few mistakes, and this printed circuit boards short circuited every now and then. So, but it was really helpful experiences and I learned a lot. The last part is the logic gates. We implemented two switches, switch A and switch B, in our circuit. According to our logic gates, if both switch A and B are closed, then all three sensors would be functioning. And if only B is closed and A is open, then only the central ultrasonic sensor would function. If only A is open and B is closed, then the right ultrasonic sensor would function, and if both A and B are open, then the left ultrasonic sensor would function. The schematic is also given here.
I'm John Burns, and here I'll describe the output of our design. The output for the user is delivered through a pair of standard earbuds. Initially, we intended to use 3D audio to indicate where the object being detected is in space. We got far with this approach, but software problems made it impossible to encode the audio files onto the Arduino. We then went to a simpler approach. An object to the left plays a tone in the left earbud, to the right in the right earbud, and straight ahead plays in both earbuds. While this is not quite as intuitive and comprehensive for the wearer as 3D audio, it still does the job of indicating where the object is. To go from the Arduino to the earbuds, we needed to do a digital to analog conversion. Our first approach was to use an external DAC chip. However, we ran into the recurrent problem of not having enough ports on the microcontroller. We then realized we did not actually need the superior sound quality of the DAC chip, as it is just the location of the tone that matters, not the tone itself. We designed a circuit using a low-pass filter into an audio amplifier. This will be used when we go to the 3D audio, when we figure out the encoding issues there. Our current prototype, again, just using the tones in each earbud, does produces sound just from PWM straight off the Arduino. We used a program called Audacity, shown here, to create some 3D audio files, but again, we're unable to actually encode these into the Arduino code. Once we solve this, it will be a large step forward in usability. 3D audio uses stereo sound, playing different frequencies in each earbud in order to place the tone such that it sounds like it's coming from a specific location, which will enable our glasses to give a much more useful output.
I am Vinamr, and I'm majoring in electrical engineering, and I'm going to talk about the control unit of our project. So we decided to first prototype it using the Arduino, and so using the inputs from the HCSR04 ultrasonic sensor, we track the distance of the objects surrounding the user from the user, and on the basis of which we decide which audio instruction should actually be heard by the user. So this was like our approach with the Arduino. Now we know that one cannot hang around with an Arduino on his glasses, and so we decided to like make our circuit on a printed circuit board using an Attiny. Now we had a number of options, and so we used a lot of factors to narrow down to one. And we classified them on the basis of the number of input-output pins, the flash storage, and that they had to be like as compact as possible. And in the end, we narrowed down to the Attiny 1634. And we also, so a lot of our members were experienced with the like how with embedded C and knew how to code the Arduino. However, like we were not very familiar with the IDE that we had to use for the Attiny, and we started to learn how to program it, and we managed to import the project files, but eventually we ran out of time and could not make like any further progress.
My name is Mohammed Khan. I'm going to be covering the results and next steps for our project. In our initial audio test, the PWM pins of the Arduino generated low quality audio when we tried using stereo audio tracks on it. In addition, we weren't able to encode some particular files, probably because of the limitations of our encoding software. We decided due to time constraints to use the ECE SR04 to test our audio circuit. The ultrasonic sensors found in the EC110 kit, the ECE SR04, 3 of them were used in our prototype. We tested them alongside code for the audio circuit previously made by Emmett in a previous project, along with the audio code which we had developed. The results are promising. Here's a video of the demo.
Okay, so this is our honors project. As of right now, we have one sensor wired up. In the future, we'll have one on the right, one on the left. So right now, if you look at me, I'm wearing headphones that are attached to the Arduino. So right now, you can see that it's picking up objects that are quite far from it. However, when I put my hand in front of it, you can see that it says there's an obstacle at the front, and the output of the headphones is beeping right now. And then when I let go, there's no sound, and then the range is farther.
The sensors would detect objects a certain range away and would play a sound, and as the object came closer, the sound would play more frequently. With 3 sensors, we would get at the very least 3 directions, right, left, and front. With this latest test, there were issues in differentiating which direction was actually the closest, so something that would be detected by the front and right sensor would play through both earphones instead of one with the other. Due to time constraints and difficulties implementing and merging the software that was provided by the manufacturer of the sensor we originally wanted to use, the CH201, we had opted to use the HCSR04. While this was our first complete prototype using both sensors and a sort of audio feedback, it was definitely a step in the right direction. Our next steps would include implementing more directions with respect to feedback and incorporating different sensors that are more compatible with the Arduino. After that, the next big step would be scaling it down to a PCB and using an Attiny and mounting it on a pair of glasses. Overall, our team learned a lot. Many of us had never used an Arduino before or had experience working on a project like this in the past. We all had fun working on this project this semester, and we'd hope to do something like this again.